And now Francesco will telling us about soundness proof for big step semantics.
Okay, so thank you for the introduction and thank you all for being here. So what I'll present today is a joint work with Riccardo Bianchini, Paola Giannini and Elena Zucca, and it is about the study of type systems and operational semantics for resource awareness. So let me start from the very beginning. So when we reason about programs, there are typically two approaches. So the first one is the extensional approach, where we basically focus only on aspects related to the input-output behavior of programs, while the other one is the intentional approach, where instead we take into account also other aspects, such as the structure of the code or the computational complexity or resource usage. So as a super simple example, let's consider these three functions. So they are clearly all extensionally equivalent because they all compute the same function, the constantly zero function. But from an intentional perspective, they are clearly different because they use the input parameter in a different way. So traditionally, the formal techniques for programming languages are focused on extensional aspects of programs. Basically, they are interested in describing or approximating the final result of a program execution. And instead, when we talk about resource-aware semantics and type systems, we want to design type systems and operational semantics to reason about those intentional aspects, and in particular to describe or approximate resource usage during the computation. So the main idea here goes back basically to Girard linear logic, and it is based on the fact that to use a resource in a program, we basically need to use a variable. And so if we manage to control variable usage in a program, we manage to control external resources. So, but now the question is, how can we measure resource usage? And the first observation is that clearly, in different contexts, we may need different notions of resource usage. And so, to accomplish this, let's say, this goal, again, adapting ideas from Girard linear logic, we parameterize the analysis on a grade algebra, which basically measures, provides a way to measure the allowed usage of variables. And so what we do is that basically we attach grades to variables to measure the allowed usage. So as I said, this is a grade algebra, so it carries an algebraic structure, which is so it may differ depending on the kind of analysis you want to do, but basically this is some form of ordered semi-ring, so we have an ordered relation and addition and multiplication with their neutral elements plus some additional axioms, which may vary. And as some examples, relevant examples, we may consider the grade algebra of natural numbers for counting the usage of resources, or the grade algebra for privacy levels, which is basically a distributive lattice to control information flow, or even the grade algebra of non-negative real numbers to measure error sensitivity. And there are many others, of course. So our contributions are the following. So basically, we study resource-aware semantics and type system for a call-by-value functional language with full recursions and equirecursive types. We want to provide this analysis without affecting the syntax of the language, so that the programmer needs not to learn a new language, basically. And we do and our formalization is based on the big step semantics, which makes the specification very clear. At least we hope it is very clear. And also this means that we need to use modern coinductive techniques to prove type soundness. So let's have a look at the syntax of the language. It is, let's say, pretty standard. It is a call-by-value functional language, so we specify it in a fine-grained syntax, which is standard for call-by-value languages. So basically, we separate the pure code from the impure code. So we have value expressions, which are expressions which cannot raise computational effects, so it cannot diverge in this setting. And these are variables, recursive functions, pairs, and unit constants, and other. And on instead, impure expressions provide standard constructs. So we have constructs for injecting values and for sequential composition. We have function application and pattern matching constructs. So coming to the semantic side, so these are the judgments. So we have two judgments, one for value expression and one for the impure expression, but they are pretty similar. And they may look a bit weird, but instead they're pretty natural, because the key idea is that the evaluation happens within an environment which maps variables to their values and to a grade which specified the allowed usage of that variable, or if you want, how many copies of the value are stored within that variable. And the key idea is that we do not use simultaneous substitution during the evaluation, but rather we substitute variables one at a time. And here the intuition is that basically using a variable means substituting it by its value. So as we will see, when we replace a variable, we will decrease its current amount by a certain quantity to track the fact that we are using it. And last, also the evaluation arrow is labeled by a grade, which basically specified how many copies of the final value we are producing. And this is because, intuitively, resource consumption depends on how many copies of the result we are producing. So if we want to produce 10 copies of the final result, we will consume more resources than when we produce 3 copies, for instance. So let's have a look at a couple of rules just to illustrate how the semantics works. This is the most important one, which is the rule for the variable. So how can we evaluate the variable? So we just look at the environment and we replace the variable by its corresponding value. But since we want to produce R copies of that value, we have to decrease the current amount of the variable by at least the grade R. So as you can see, resource consumption is fully non-deterministic, so we only provide a lower bound to resource consumption. And the other thing which is important is that if we do not have enough resources, so we do not have enough copies of the variable, we cannot apply this rule, and so the computation is stuck due to resource consumption. This means basically if we need to produce 10 copies of a value and we only have 3 copies of that in the environment, we cannot apply this rule. Another rule which is quite interesting is the rule for the application, because it shows the interaction between recursion and resource consumption. So to evaluate a function application, we need to basically first evaluate the first argument, producing a recursive function, S copies of the recursive function. Then we evaluate the argument, producing T copies of it. And then we have to evaluate the body of the function, but in an environment which is extended by the argument of the function and the function itself, because the function is recursive, may be recursive, and so it may need to call himself during the evaluation of the body. And as you can see, so in the environment, the parameter is added exactly with the grade T, which is the number of copies we have produced of that value. But the function is added with a grade which is not exactly S, but slightly, let's say, less copies of the functions are added to the environment, because some of the copies we have produced are consumed to perform the current function call, basically. So here we are calling the function, so we are using it, and so some of that copies must be consumed here. Again, everything is fully non-deterministic, so we do not give many constraints on the resource consumption. So to see what happens on a, let's say, concrete example, even if it is quite simple, let's consider this simple function, which basically consumes the resource, the external resource y, and then recursively call the function on the input. So this clearly is expected to diverge. And to see this, we try to build an infinite derivation using our rules. So we start evaluating the body. So we first consume the variable y, and we decrease its corresponding amount in the environment. And then we evaluate the function call. And to do so, we extract all the copies of the function from the environment. We extract all the copies of the argument from the environment. And we perform the function call. So we start evaluating the body in the extended environment. And as you can see, we have to consume a certain amount of the copies of the function. So this process clearly can go on forever, but to do so, we have to, basically, at each step, this imposes an equation which must be satisfied to be able to build the infinite derivation. And this equation clearly has a solution only if the initial grades of the function and of the external resource y are intuitively infinite, because we have to use them infinitely many times. Okay, that's all I wanted to say about the semantics, but let's have a quick look at its type system. So the type system is, types are defined by, are coinductively defined by these productions. And so we have, we use coinductive types to have a simple way to encode basically equirecursive types. And we have two productions, one for plain types, which are the standard ones, so arrows, the tensor, and sum, and the unit type. And we also have graded types, which basically are types decorated with a grade, which specify that they allows usage of the values of that type. Look also, it is important to notice that the, let's say, plain types, type constructor are applied to graded types because we have to specify the allowed usage also of components of more structured types. And another important thing is that the arrow types has also a third annotation which specifies the recursion grade. So in the type, we say basically how many recursive calls we expect, or in which way we expect the function is recursive. So if that grade is 0, the function will be not recursive. Otherwise, we expect this grade to be infinite because we have to over-approximate all possible recursive calls. And the structure of the typing judgment is this one. So I report it only for expression, but the one for value expression is the same. So basically, this says that the expression E produces a final result which must be used at most in R mode or with grade R, or at most R times. Think of it depending on the kind of application you are using. And to do so, uses external resources x1, xn, according to the specified grade in the context, which are R1 and Rn. Okay, so just a couple of typing rules. The rule for variable, so an important thing to notice is that these typing rules are substructural because, let's say, we are inspired by Girard linear logic, so we don't have a top-down approach, but rather a bottom-up approach, if you want. And to type the variable, the context contains only the variable we are using. Sorry? Okay. We have only the variable we are actually using because no other external resources are needed. And instead, for typing more complicated term, we have to combine the contexts using the algebraic operations of the grade algebra structure extended to context in the standard pointwise way. Okay, type soundness. So it is well known that in big step semantics we cannot even express type soundness because we cannot distinguish between stack and non-terminating computation. And so to be able to prove a type soundness result, what we do is we rely on recent results and we basically apply a canonical construction which allows us to explicitly model divergence in big step semantics, relying on generalized inference systems, and provides us a standard proof technique, a coinductive proof technique for type soundness in this extended semantics. And in this way, we can express the type soundness property in a pretty natural way. So we say that if a configuration is well typed with grade R, then the configuration evaluates with that grade to a final result, which may be either a value with an environment or divergence. And this means that there exists a computation which is not stuck due to resource consumption. So it is a soundness may result, which is because let's say the resource consumption is fully non-deterministic, but it is standard in resource semantics. So that's all I wanted to say about this work. If you're interested in more details, let's check the paper. Concerning future work, what we are currently investigating, so the grades, as I described you, basically give an approximation of the local usage of resources in a term. But in many cases, we may need a way to specify assumption that the term need on how the environment uses the same resources. And we are investigating the possibility of using grades to specify such assumptions. And this would hopefully lead us to a common generalization with uniqueness types, which are quite used in the literature. So that's all I wanted to say. Thank you for your attention.
Okay. Okay, if we have any questions, please come to the mic in the aisle. Yes? Here on the two sides. Okay. Yep, go ahead.
Hello, thanks for the nice talk. You presented a call by value calculus, and the thing is that with something like call by push value, the idea is that you could get semantic for free, basically, for both call by value and call by name, and also it has a nice presentation as a linear polarized calculus. So I wonder if you look into extending this to call by push value, and if you foresee any difficulties.
Oh, so actually, we haven't looked at the call by push value strategy yet, at least, but for sure it is an interesting perspective. I'm not really an expert on that field, but it may be possible. So the honest answer is I don't know, but I'm really interested in discussing it if you want.
Okay, thanks.
Thank you.
Okay, and one more question.
Yes, thank you for the talk. I'm over here on the other side.
Sorry.
That's okay. So your cost measure here, or resource consumption measure, is uses of a variable. How would this change? Would it be feasible if I were interested also, or alternatively, in uses of operators? Like I want to know how many floating point additions my code did, or whatever.
So you mean you want to count basically the...
I want to count operations rather than variable uses.
Yeah, it's more like it's more like on the effect side, I guess. So these are more on the co-effect side. It's at least I don't know. I'm guessing, but to me, so my feeling is that it's more. It's something more like a dual setting, counting the number of operations. But I don't know. It's because I don't know where to attach the measure basically in the typing context in that way. I imagine this more like an annotation of the old judgments, which says how many.
Okay.
Okay. Well,
Thanks.
Let's thank Francesco.